Good morning. In today's session, I am going to explain you some more examples for Coulombs law. Note down the problem. Find the charge, both magnitude and direction. Find the charge placed at the center. Placed at the center so that the system is in equilibrium. So that the system is in equilibrium. So, the problem given is like this. Say this is a square of side A, that is a square of side A. 4 identical charges plus q each are placed at the 4 corners of the square. You need to find out the charge placed at the center so that the system is in equilibrium. So, here system is in equilibrium when net force on all individual charges is equal to 0. So, let us try to find out the charge placed at this corner, force on the charge placed at this corner. So, this is the charge on which we are going to find out the net force. For the time being, forget about this charge. So, we want to find out the net force due to these charges at this point. So, let us name the corners, this corner as 1, 2 and 3. See, due to this charge, force is repulsive, it will be in this direction. So, F1 is equal to 1 by 4 pi epsilon naught Q1 Q2 by distance. Distance is root 2a. Distance between opposite corners is nothing but the diagonal length of the square here. That is root 2a whole square 2a square. So, F1 is 1 by 4 pi epsilon naught q square by 2a square. Now, F2, it will be along this direction. F2 is force on this positive charge. Due to this exerts repulsion. So, this is F2. Similarly, due to this charge, force is repulsion. This is F3. So, F2 is equal to 1 by 4 pi epsilon naught Q1 Q2 is q square. What is this distance? It is a. So, q square by a square. Let us try to find out the force on this due to this. 1 by 4 pi epsilon naught Q1 Q2 is q square. This distance is also a, it is a square. So, F2 and F3 are equal in magnitude. Now, these two are equal in magnitude, this and they are at right angles. So, when two forces of equal magnitude are at right angles to each other, then the resultant force is root 2 times 1 by 4 pi epsilon naught q square by a square. That is the resultant of 2 and 3. 1 by 4 pi epsilon naught q square by a square root 2. And that will be along this direction because that will be the angular bisector. Now, if you watch this, this is F23. So, the net force on this charge becomes F1 plus the resultant of these two is also along the same line. When two forces are in the same direction, net force is equal to the sum of their magnitudes. So, we can take 1 by 4 pi epsilon naught q square by a square as common factor. F1 1 by 2, F2 root 2. So, the net force on the charge placed at this corner is that much. Now, our aim is we want to keep the system in equilibrium. So, the system is in equilibrium only when the net force on the individual charge is 0. Net force on the individual charge is 0. So, here to make the net force on this 0, the charge placed at this should exert a force in this direction which should exactly balance the net force. So, this is positive, the charge placed here should attract this. So, it has to be negative. Let us take its magnitude as Q, X. So, force between these two charges I am finding out. Look here. To keep the system in equilibrium, the charge placed at the center should balance this force. So, it has to exert a force in this direction. So, this charge can exert a force in this direction, that is attraction only when it is dissimilar. So, as the charge placed at this corner is positive, this has to be negative. One point is confirmed, nature of the charge is confirmed. Now, let us try to find out the magnitude. Force between these two, that is 1 by 4 pi epsilon naught Q into X by distance between the corner and the center of a square, A by root 2 whole square, A square by 2. That should balance this net force, that is 1 by 4 pi epsilon naught Q square by A square half plus root 2. So, 1 by 4 pi epsilon naught Q by A square gets cancelled, X is equal to Q by this 2 into 1 by 2 plus root 2. And we have already proved that the charge has to be negative. So, in order to keep the system in equilibrium, the charge placed at the corner of the at the center of the square must be minus Q by 2, 1 by 2 plus root 2. Okay? I will explain two more similar models so that you will be perfect as far as this concept is concerned. Now, again, note down the problem. Find the charge placed at the center of an equilateral triangle so that the system is in equilibrium. So, you note down the problem. Find the charge placed at the center of an equilateral triangle here. Find the charge placed at the center of the equilateral triangle so that the system is in equilibrium. The system has three identical charges plus Q placed at the three corners of an equilateral triangle of side A. In order to keep this system in equilibrium, what is the charge placed at the center? That is our challenge now. For the time being, let us forget about this. Actually, as I told you, equilibrium always implies that the system is in equilibrium when the net force is equal to 0. System is in equilibrium when the net force, equilibrium implies net force is equal to 0. Net force on every charge must be 0. So, let us try to find out the force on the charge placed at this corner. So, let us name this corner as 1, this corner as 2. So, on this charge, this exerts repulsion in this direction, this charge also exerts repulsion in this direction. So, both those forces F1 and F2 are equal in magnitude, that is equal to 1 by 4 pi epsilon naught Q1 Q2 by this distance is A square. Those two equal forces are at an angle 60 degrees. When two equal forces are at an angle 60, the resultant is root 3p. So, the resultant force acting on that is root 3 times 1 by 4 pi epsilon naught q square by a square. Till then it is clear. Now, what we want to find out the charge placed at the center so that the system is in equilibrium. Here what is the charge placed? So, on this the net force is acting in this direction, the resultant. So, this should exert a force in this direction. Here we placed a positive charge. If the force is towards this, that has to be attractive force. So, this charge must be negative. That is confirmed. Let its magnitude be x. So, force between these two forces charges is 1 by 4 pi epsilon naught qx by this distance is a by root 3 whole square. Because distance of each corner from the center of an equilateral triangle, those fundamentals you must have on your tips. If you do not have them, the problem is gone. So, distance of each corner from the center of an equilateral triangle is a by root 3. So, this distance square, a square by 3, that force must balance the net force, that is root 3 times 1 by 4 pi epsilon naught q square by a square. 1 by 4 pi epsilon naught q by a square gets cancelled. X is equal to root 3 q by 3, or it is q by root 3, and it has to be negative. So, the charge placed at the center of that equilateral triangle so as to keep that system in equilibrium is minus q by root 3. Okay? Now, I am going to give you another problem which is already given in previous examinations. Note down the problem. Find the charge placed at the midpoint of line joining two charges plus q each. That is the question given. Find the charge placed at the midpoint of line joining two charges plus q each. This is plus q, this is plus q. Let this be the midpoint. What is the charge placed at this point so that the system is in equilibrium? So that the system is in equilibrium. So that the system is in equilibrium. So, two identical charges plus q each are separated by a distance r. What is the charge placed at the midpoint of the line joining the two charges so that the system is in equilibrium? Concept is same. The system will be in equilibrium only when the net force on individual charges is equal to 0. So, here for the time being, let us forget about the charge placed at the midpoint. So, on this charge due to this, force F is equal to 1 by 4 pi epsilon naught q1 q2 is q square, distance is r square. It is in this direction. Now, the charge placed at the midpoint should exert a force in this direction so as to neutralize this force, then this will be in equilibrium. So, this must also be equal in magnitude F and it is towards the charge. So, this charge needs to attract this one, so it has to be dissimilar, that is why it has to be negative. Let its magnitude be x. So, the force between these two charges becomes 1 by 4 pi epsilon naught q into x by this distance, as this is the midpoint, this distance becomes r, r square by 4, that should balance this force, that is 1 by 4 pi epsilon naught q square by r square. So, 1 by 4 pi epsilon naught q by r square gets cancelled. From that, x is equal to q by 4. From this, it has to be negative. So, the charge placed at the midpoint of two identical charges plus q each is minus q by 4. Then the entire system will be in equilibrium. So, I will stop here for today. Thank you and bye-bye. Thank you.